theorem is not a mathematical one. It's more about explaining a collision. So using the impulse momentum theorem to take a look at a collision and explain why is the force really high, or what happens as the force increases, or what happens to the time of a collision if the momentum change increases. So basically, what happens to one of the variables if another variable changes? We're going to discuss this using the idea of a car crash. Specifically, car crash with an airbag. The idea behind airbags is they use the impulse momentum theorem to minimize injuries. I mean, that's the whole point of an airbag. You're trying to minimize injuries. How is it that an airbag minimizes injuries? A lot of students like to say, oh, it's because it spreads out the force. And there is a bit of that too, because when we talk about pressure, so actually I'm going to take a little side note here and discuss pressure. Pressure is equal to a force over an area. So if you increase the area, the pressure would go down. You're not really changing the overall force, but it's more that you're increasing the area, so the pressure goes down. So when you talk about increasing the area, you're not talking about changing the force, actually. You're talking about changing the pressure that someone feels. But airbags actually do manipulate the force involved. And how they do it is by changing time. So let's take a look at the impulse momentum theorem equation again. So that's this guy right here. So impulse momentum theorem says the change in the momentum is going to equal the average force experienced times the change in time. Now here I say without an airbag. So the idea is if you did not have an airbag, and so the person is going to be hitting the car dashboard or the steering wheel, no airbag, hitting something very, very hard. What's going to happen is they have to, regardless of whether they have the airbag or not, they're going to have to change their momentum from some kind of momentum greater than 0 to 0. So either situation has the same change of momentum. But what's different is without an airbag, the time that the collision takes, and remember that this T here is specifically the time of collision. The time the collision takes is much, much shorter without an airbag than with an airbag. Because what it's doing is, this airbag is pushing back, starting right here. But as this person's head goes further in, it's going to continuously push back and push back and push back. So the whole time that it's in contact with the person's face, it's going to be applying a force over that entire duration. Whereas if there was no airbag, this person would only have a force being applied once they hit the steering wheel. And the steering wheel is not gonna move. So that means this collision lasts fractions of a second, or much less than the collision with the airbag. That's the cushioning effect. So the cushioning effect, what it does with the airbag, the cushioning effect increases the time that the collision takes. And the longer that a force is being applied, the less force actually needs to be applied to get the same change in speed. Because remember, we're trying to get the same change in speed as with or without the airbag. But if we apply the same force over a longer period of time, we won't have to apply such a great force. So the force needed to slow the person down decreases because the time increases. Remember, the left side of this equation is not going to change. So if you increase the time, but you're going to have something that decreases on the right side in order to balance this out. Another thing we could do is solve for the average force. So if you solve for the average force, what you get is that the average force equals the change in momentum over the change in time. If we increase the time, that increases the denominator of a fraction. And if you increase the value of the denominator of a fraction, you decrease the overall value of the fraction. Larger denominator, smaller value. And if you decrease the top, you would also decrease the value. So there's two ways. If your goal is to minimize the force that something feels, there's only two ways to do that. You increase the time, or you decrease the momentum change. Now, notice I'm specifically talking about the force. You could change the pressure that something feels. And that would have an important effect. That would still cause less injuries. So a combination of decreasing pressure and decreasing force would create the most ideal situation for stopping something without damaging it. And notice, if you decrease the force, you're also going to be decreasing the pressure because force is in pressure. This is a meme right here that is often circulated around the internet. I've seen it on shirts before. You have a person falling, and they say it's not the final velocity. We should notice that this is the equation we've dealt with before, which is the final velocity is equal to the initial velocity plus acceleration times time. So it's not the velocity that kills you. It's the force, which equals the mass times the change in velocity over time, which if you just put this mass into the change of velocity, that's change in momentum. That's this equation right here. So now you can understand whenever you see this meme pop up on the internet or on someone's t-shirt. I leave you with a practice problem because remember, what we're trying to do here is we're trying to explain a collision or explain the dynamics of a collision using the impulse momentum theorem. So what I want you to do is specifically reference the equation and maybe draw up arrows and down arrows for things increasing, decreasing, and then talk about what's happening. So with that, you're going to think of a collision that's involved in maybe a hobby, a sport, a game that you enjoy, maybe a scene in a movie. Anything. Anything that's not an airbag, because I've already done that one. So pick something else. Something that's related to a hobby of yours, or a sport, or a game, or like I said, maybe a movie scene or something you enjoy. I want you to explain how big the force is. Now, of course, you don't have numbers, but you can do in relative size, like big force, medium force, small force. Most importantly, I want you to be able to justify your answer using the impulse momentum theorem. So the idea is that you're going to use that equation to explain why do you think the force experienced is large, medium, or small.